Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at information from the Chapter 8-9 test to clear up some misconceptions and reteach some concepts. Some common errors and misconceptions. Lattice energy. Drawing Lewis dot structure is an incredibly important idea for this upcoming test because it's really where you start most of your problems. Concepts related to electron domains, molecular geometry, hybridization, really the only math from the chapter that you're going to need to worry about, which is calculating delta H using bond enthalpies. Then finally, a little bit about resonance. So those are the ideas that we're going to be looking at here. Now, first off, lattice energy. What law explains lattice energy? So what do we use when we're discussing lattice energy? And remember, lattice energy is the energy involved in the strength of ionic compounds. So it's the amount of energy it really would take to break an ionic compound apart. Well, it's governed by Coulomb's law because what we're looking at here is an electrostatic attraction, and electrostatic attractions are governed by Coulomb's law. So what two factors affect lattice energy? Well, right out of Coulomb's law, you're looking at the ion charges. So the greater the charge difference, the greater lattice energy between the ions. And then finally, ion size. Since in Coulomb's law equation, distance is on the bottom between two things and it's squared, that would be the increase in size is a decrease in lattice energy. And of the two, which is really more important? And this is a really important idea related to this because when you're seeing things related to ions and things related to both charge and size, you really need to be able to determine which one is more important. Well, because of the differences in ion size are very, very, very small quantities, really it's much less important than the differences in ion charge. So the most important idea in terms of Coulomb's law and how it affects lattice energy is really evaluating the charge difference first. So if you have a +1 -1 and another compound is a +2 -2 or even a +1 -2, then that's going to be a much more important factor than really the small changes in size. So while change in size is a inverse square relationship, the actual distances we're talking about are so small, ion charge becomes much more relevant. And then finally, how are they actually calculated? Well, we don't do a lot with the Bohr-Haber cycle, but you need to understand the principle behind it. This is how we calculate lattice energies. It's really an application of Hess's law. So what we're really looking at is how, by looking at a variety of ionizations and formations and electron affinities, we can determine what the lattice energy is for a variety of different ionic compounds. And while it's not a calculation that you're going to be doing, it is a calculation that you need to understand. It's really an application of Hess's law, and it's a fairly simple way, although when you look at the math, it's much more complex than the level of understanding you have to have about it. It's really a fairly simple way to calculate the actual lattice energies of different ionic compounds. Second idea that I want to look at is really drawing Lewis dot structures, because this is a core to chapter 8 and 9, and it's something that you have to be able to apply and use this consistently. I've seen it in too many situations, sometimes even good students trying to shortcut around this. You have to apply the process. You need to know what to do and apply it every single time. You can't just jump to, I think it's this. So first thing you need to do is count valence electrons. And remember, watch out for your polyatomic ions, because if you have a negatively charged ion, that means you have extra valence electrons available for bonding. And if you have a positive polyatomic ion, that means you are short. So you have to subtract out whatever the charge is from your total electrons. So first you need to find out how many electrons do I have involved in bonding. So that would be your valence electrons. So remember, this is our pool of electrons that are going to be involved in what's happening when we form our molecule. Next thing you need to do is draw your center atom surrounded by the outer atoms and then connect with single bonds. Now remember, the center atom, it's the one lowest in electronegativity, but typically it's much easier than that. You just look for the one there's only one of and put that in the middle. And remember, you're never, ever, ever going to have hydrogen as a center atom because it only forms one bond, and that's it. That's all it can ever do. Now, once you determine how many single bonds you need to connect all of your outer atoms to the center atom, remember each of those bonds is 2 electrons, and you need to subtract that from your total pool. So what you're finding out is how many of my electrons are going to be involved on the surface, because it might change when you get to the end. with bonding. Third thing you do is add octets to the outer atom. This is a critical step. You cannot add octets to the central atom until the final step. So first you add octets to all of your outer atoms. Remember, hydrogen doesn't need any more with the bond. And then you subtract those from the total to see where you're at. Now, if you are done at this point, then that means everything should have a full octet. But in most situations, you're going to, or not in most situations, but in some situations, you're going to need electrons on your center atom. So if you still have electrons left, you would add those electrons to the center atom and then subtract that from the total. Now, at that point, there's a couple of things that might have happened. You might have extra electrons. And if that's the case, add them to the center atom, and what you have is an expanded octet. So after giving your central atom its full octet, and all of your outside atoms their full octet, if you still have electrons left, they're going as electron pairs on the center atom, and what you have is an expanded octet situation. Remember, that would be period 3, p block, and lower can expand octet. Now, the trickier one is if you're short electrons. Now, if you're short electrons, first thing you need to ask yourself is this beryllium or boron family? Because if that's the case, then you will have a deficit octet situation, and you need to recognize this here. Just don't automatically pull an unshared pair and multiple bond. If you've got something that's an exception to the octet rule, like beryllium and the boron family do, then at that point you would be done. You would have less than a full octet on that center atom. But in all other cases, you're going to pull an unshared pair from an outer atom until you have a full octet. Now, which outer atom do you use? Well, it really depends upon the situation. I mean, if you've got hydrogen there, of course, there's no electrons to pull, so it's going to come from something else. And in most other situations, you'll realize where it looks like you have a choice, well, all the choices are equal. So you've got 3 chlorines to pull from. You've got, or I should say, 3 oxygens to pull from. Um, in that particular case, then you're going to have a multiple bond type situation. So from one of your outer atoms, you're going to take an unshared pair and make it a shared pair. And if at that point you have full octets everywhere, you're done. If you still are short, that means you need a triple bond. So you're going to pull another pair of electrons. Drawing Lewis structures, I can't emphasize this enough. This is the most critical concept on the entire test to be able to apply, because so many questions will begin with being able to draw an accurate Lewis dot structure. So being able to apply these rules consistently and accurately is really critical to this test. Now, next idea, once we've got a Lewis dot, you need to understand the concept of electron domain, because we use it for a couple of different things. So let's say we've got a couple of sample substances here. Um, in the first case, we have a single center atom with 2 outside atom situations, a double bond, a single bond, and an unshared pair. Remember, each of these is an electron region. So we've got 1, 2, 3 electron domains in this first substance. So electron domains are electron regions. A single bond counts as 1, each unshared pair counts as 1, and all multiple bonds count as 1 overall. Now, the other situation here is a linear situation with 1 center and 2 outside atoms, and we've got a single bond and a triple bond. Remember, I just said single bonds count as 1, and all multiple bonds count as 1. So this has 2 electron domains total. So counting electron domains is critical for hybridization. It's the first step in looking at molecular geometry. It's critical for a number of different things. So make sure you can count electron domains. Now, the second thing you need to be able to do with electron domains is understand their geometry, and I also put in this in here as well. Remember the base bond angle that implies. So when you take a look at the first situation here, well, we've got 3 electron domains. 3 electron domains is a trigonal planar, 120 degrees base angle. So each of these bond angles, and really here we only have one bond angle, should be 120 degrees. But you need to understand the electron pairs here have a role in what happens to that 120 degrees. Now, since this double bond repels more, that would increase it above 120, but this unshared pair also repels more, and that's going to push it back. So if you had to guess, you would say this is going to be around 120 degrees based on that situation. Now, the other one, we had 2 electron domains. That's a linear 180. So that's exactly what that's going to be. That bond angle would be 180. So you need to understand how the number of electron domains transfers to an electron domain geometry, and you need to also understand what the degree angle is. What is the base degree angle in those bond situations? So if we had another situation here, so if A with a single bond, and a double bond, and each of these would be an outside atom. We have 3 electron domains, so that's a base trigonal planar. And if we're looking at this bond angle right here, well, because this double bond repels more, that's going to increase this angle and that angle and decrease this one. So over here, we're going to end up less than 120 degrees. And on both of these other bond angles, we would be greater than 120 degrees in each of those spots. So with electron domains, you should understand how to count them. You should understand what the electron domain shape is, and you should understand what the angles are approximately between them. Not exact numbers, but you should know the base number and whether it increases or decreases from there. Next idea, molecular geometry. First off, you need to understand that this is based upon the electron geometry. Now, sometimes they're the same and sometimes they're different, but they're only going to be the same if there's no unshared pairs in the center atom. If you don't have any unshared pairs, your electron domain geometry and your molecular geometry are going to be the exact same. If there are unshared pairs, instead of, let's say, trigonal planar, if there's an unshared pair there, it's going to go down and go into the bent category. So the unshared pairs are really the key to looking at molecular geometries. If there's none, electron domain and molecular geometry are the exact same thing. If, however, we have unshared pairs, you don't see all of the electron domain geometry, and that's going to move you, a way to look at it is down from there. So if you had a um, trigonal bipyramidal type situation, that would be 5 electron domains. Well, if I lost one electron domain, that's going to push me into the seesaw. If I had another electron domain, that's going to push me into the T shape. If I had another, that's going to push me into the linear. So all those are less than that trigonal bipyramidal started out as. So you need to understand your electron domain geometries and how they impact molecular geometries. And it's all about the electron domain and the number of unshared pairs in the center. And be careful of the one I mentioned. The electron domain geometry is trigonal bipyramidal. That means the unshared pairs must be on the equatorial region. So if I have my base electron domain geometry, which is one above and below, 180 degrees apart, and then in my equator region, I have 3 120 degrees apart. If I have unshared pairs, they have to go in this region first. And that's going to affect from seesaw to T-shape to linear as I add unshared pairs of those. So be particularly careful of the trigonal bipyramidal when you're looking at molecular geometries. So unshared pairs, remember, must be in the equatorial plane. Now when you have the octahedral situation, which is 1 above and below and 4 in the equatorial plane, here they're all 9 degrees apart. So the first unshared pair can go anywhere. The only restriction for this one is if my first one goes here, my second one has to go directly opposite, and that throws us into the square planar. Next idea, hybridization. First off, what is it? You should understand the conceptual idea behind what hybridization is. Well, it's a blending of atomic orbitals to make equal energy molecular orbitals. And this can be through overlap or it can be through a hybridization type situation where you're actually mixing the old S and P orbitals into new equal energy orbitals. And the basic idea behind this is if we have something like water, which is H2O, in H2O, we have 4 electron domains. And all 4 of those new electron regions have to be equal in energy. So how would that come about? Well, if I blended an S and 3 of my P's from before, that would give me a total of 4 equal energy orbitals. So they would blend to form 4 sp3 hybrid orbitals. So you need to understand that electron domains each have to be equal in energy. And how do you determine your hybridization? Well, just what we looked at. Remember, the key is it's based upon the number of electron domains. The second part of this is you need to understand how you add things together to get it. Remember, you're going to have one S, And then you have up to 3Ps. You use how many you need. So if it was a linear situation with a single bond and a triple bond, this is only two electron domains of equal energy. So that would be an sp hybridization. So I would end up with two sp hybrid orbitals. Now, what's going on with the other bonds? Well, remember, these hybrid orbitals are our sigma orbitals here, equal energy sigmas. Well, if I have a multiple bonds, that means I have the overlapping above and below the bond plane P. And if I have a triple bond, I have an overlapping in front of and behind the bond plane P. So remember, these are both pi orbitals in this situation. But as far as hybridization goes, it's really just count your electron domains and keep adding s's and then p's, but you only have three, and then if you need them for expanded octets, you're going to pull some d's. So that's really the key to hybridization. It's a blending of atomic orbitals to make a number of equal energy orbitals, and that number equals the electron domain. That's really the key for hybridization. Next idea. It's only math really that we're going to do from the chapter, because technically with the Born-Haber process, you could do math. There you just need to understand what it is. It's how we calculate bond, the bond enthalpy of an ionic bond, so it's a lattice energy. And you need to understand it's really just an application of Hess's law. Well, the math that you need to be able to do is the other alternative route to calculating enthalpy changes. And in my opinion, this is something that the AP test has been stressing more and more and more in the past few years. So this is even more likely to happen on the AP test than is something like formation enthalpy calculations. So this is one you got to be comfortable with. So you know you're going to see a few of these on the test. Now, the first thing about doing delta H's for reactions, you got to draw the electron dot for each substance. You need to be able to see all of the bonds. So first, draw your electron dots, just like you do with most problems in the test. Draw your accurate electron dot for each particular substance. And then don't forget, when you're looking at the next step, break them all, make them all, you need to take into account the coefficients in the balanced equation. Because technically, if it says 2H2O, you then have two H2O molecules, which is four O to H bonds that are going to be involved. So count up all your bonds and bond types, and then multiply by the coefficient of the balanced equation. And then just break every single bond and then make every single bond. Don't split hairs and try and worry about what's actually breaking and what's actually being made. It adds an extra step of complexity. Just count them. That's all you got to do is see how many bond types you've got on each side. And once you draw your loose dot structures, that's a lot easy. And then figure out based upon what's in the electron dot picture and what's in the coefficient of the balanced equation, how many of each type of bonds you've got on each side. And then just break them all, make them all. And then remember, when you're done, you're going to take your total amount of your reactants and subtract the total amount from your product side. So do reactants minus products. And it's not really that you're subtracting, it's just that when you look up bond enthalpies, they're all energies required to break. So they're all from the breaking point of view. Well, the making point of view, it should be opposite. So those should be negative. And that's what the minus takes care of here. It makes appropriately the stuff negative. But this is a type of calculation you need to be very, very comfortable with. Next, and finally, resonance. Really, what is resonance? Well, it's an idea that you've heard about for 2 years, so everybody thinks they get it until you have to answer questions about it. So you need to be very clear on a few things about resonance here. First off, resonance is when one Lewis structure will not accurately portray the molecule. So you've got a situation where you have NO2 minus, and when you draw it, it ends up looking like this. Well, it could also just as accurately be drawn like this. So this is a situation where we have resonance. So what really happens is it's an average between these two structures, and that's what we mean when we draw both of them and then connect them by a double arrow. It looks like this double bond, which is delocalized pi bonding, that's our key idea here, is this pi bond that we're looking at here is not localized, it's delocalized partially in both positions. So it's the average of the two. So what we really end up with is 1.5 bonds and 1.5 bonds in the picture. So that's what it is. The second thing, when does it occur? Well, this is one that more people are comfortable with. Remember, it occurs when you've got an equal choice about where to put a double bond. That most people are comfortable with. But these ideas in here, Sometimes people are a little more hazy on those. Make sure you clearly understand what's happening with resonance. And that finishes our notes dealing with help over the next test. Good luck.